Hello, everyone. My name is Alex Matrosov, and I'm happy to present today on the GrayHat conference. I have a very interesting topic to discuss with you today, and it's blind spots of threat intelligence tied to hardware and firmware. Basically, I want to discuss the challenges which we have to gain invisibility on the hardware and firmware levels, and why actually I can cover these topics just because I spend a lot of years doing this kind of research. I'm leading offensive security research at NVIDIA at the moment, and I did a lot of different security research and tied to different hardware vendors in the past. And also I'm doing security research since 1997, mostly focused on the beginning on reverse engineering, advanced threats, and malware, but switching my focus in the direction of the hardware and firmware security about 10 years ago. So let's discuss why these problems is very important, and actually it's getting more important in the moment because it's just getting worse, and attackers start abusing let's say blind spots of the industry on these kind of threats. So first of all, look on this picture. And we have kind of like security industry visibility point where all the modern endpoints very good on the detection and very good understanding of the threat landscape. But also we have modern persistence techniques, which is basically under the water and actually invisible for most of the vendors. And think about how many vendors actually covering hardware and addressing the hardware and firmware threats. And actually, I would say not much, and most of them focused on known attack vectors, and they not really have experts on these fields, which is developing the mitigations and detection methods, which is meaningful. So if we talk about persistence, let's have some introduction what kind of types of persistence we have. And classical endpoint solutions covering boot sectors, bootloaders, file systems, operating system level. Basically, I would say it is covering operating system and some of the boot parts of the boot process on the later stages. But hardware and firmware, usually it is still a blind spot. So basically, we have a lot of different things which can be applicable and come from the firmware level. And basically, this kind of threats is still invisible. And if we think about what is industries detecting from the known threats coming from the public news. And recently, Kaspersky Lab detected mosaic regressor UEFI implant, which was based on the hacking team Vector EDK, which is known at least for 5 years. And actually, they use exactly the same indicator of infection of the systems with UEFI variable named FTA. So this indicator literally 5 years old, and it's still able to provide some persistence for the attackers. And one of the things which is actually really surprised to me, it was mosaic regressor make a lot of noise. Yes, the threat is interesting because it's tied to the firmware, get detected in the wild. But if we think about this, this threat is really lame. So it doesn't have any new techniques used there. It doesn't have any types of infection methods which is used there. So basically, we detect what was known and very old. And even like LoJack's implant, which was detected by ESET, was more advanced compared to mosaic regressor, but still was not using anything new. LoJack's just used, which was known and actually already very well explained on the public. So also, if we think about why these problems exist, why we don't detect anything new. So first of all, defensive technologies coming from the hardware vendor side, in many cases, disconnected from reality. Basically, people who is architecting these security features, they not really understand how real threats is working and how the attacker techniques and tactics is appears in reality. And on the other hand, we have endpoint vendors which don't understand enough of the firmware specifics. So basically, most of the classical endpoint solution vendors mostly trying to apply the same approaches which they're using on the operating system level. But the firmware world is very different, and a lot of different things exist on this level, and just trying to think in the same way as we think in an operating system level detection, it is actually wrong direction. We're missing a lot, and we don't cover specifics of this execution environment. If we think about like what we have currently to describe techniques and tactics of the attacker, you will be always think about MITRE attack, right? So framework. And on the firmware, we have most of the impact and detections, which is recommended, it's basically tied to the operating system level. And as example, we have also boot integrity, but boot integrity doesn't guarantee visibility of the threat. And if we talk about privilege account management, OS privileges not equal to the firmware level privileges. And of course, why updating the firmware, you think you download and update your firmware from the trusted source, and you basically have a secure update in this case. So it's no guarantee. And it's why actually we have all these problems around, because also we don't understand much how the impact from the firmware level is coming to the operating system level. So, and broken integrity, of course, doesn't say much about the actual impact and what you have as inside the firmware, what kind of implant or modification or malicious activity coming from there. We don't have enough signals coming from the firmware and hardware like we collecting from operating system level. I was talking about that actually last year in my keynote, the Advanced Threats Evolution Research Arm Race. And still, I don't see the industry is shifting much in this direction. And I would say without collaboration between hardware vendors and firmware owners and actually endpoint industry, it will be no way how it can be developed meaningful solutions. Basically, we have three different worlds: firmware, hardware, and operating system level, and all of them have weak security policies and transitions between them. And these three different worlds mostly disconnected from each other. So basically, we have a platform boot process, which is start from the hardware and come to the operating system level. And we have actually lack of threat intelligence signals, which is actually increasing, go down to the stack, tied to the hardware. Nowadays, it is hard to spot real boundaries between actually hardware and firmware and operating system level, because basically we have hardware which is passing control to the system firmware, and system firmware, it's actually looks like a real operating system and doing most of the job, and just on the later stage of the boot, passing control to the bootloaders. So, but if we think about the number of reported issues for the firmware, it's significantly increasing every year. The statistics came from National Vulnerability Database, and if you look on the numbers of the threat, so it's actually increasing every year. Also, on another side, as I mentioned before, not all the security architects understand correctly how the platform transparency should be implemented. As example, look on this screenshot from UEFI forum presentation. So it's saying threats can be identified by analyzing the security requirements and platform diagram. Yes, it can be on the theoretical side, but honestly, it is very hard to spot the problems on the requirements and diagram. So basically, you need to have the real system, you need to analyze the code, you need to understand the architecture, and only this transparency actually can provide the confidence on the visibility level. So on another side, we still have a lot of security through obscurity, and actually it's evangelized by firmware and hardware vendor. So we have a lot of different things which is just not documented. As example, we have Intel BIOS Guard and Intel Boot Guard technologies, which is being publicly available with some details just because researchers reverse engineered them and may create some of the blog posts and documentation about these technologies. But the vendors still don't publish an actual reference documentation about these technologies. And please don't do the binaries, share the technology specs and make this more transparent for the industry, because security through obscurity doesn't work, and we know this. We learned these lessons from the past, right? So, but why we doing the same mistakes now, right? So also, if you want to learn more about rootkit and bootkits, pay attention in my book, Reversing Modern Malware and Next Generation Threats. But it's not about the book. Look on this picture. I really like this cover. Basically, it is a Kraken, and it is a guy, a little guy on the boat, which is trying to escape from the Kraken, right? So in this case, it is a really persistent threat inside the hardware or firmware, and the security architect, which is trying to survive in this very offensive world. So, but on another side, we have actually a lot of problems with security boundaries. We have different components across the system platform with different firmwares inside, right? And all these components actually threat modeled separately. So, but in the same case, we have most of these components based in the same security boundary. What that means, if you attack one component, it is easier to attack from this component some more secure components around platform. So, and I believe currently this creating just more and more complexity on top of the system platforms and more components available. And this situation getting worse in terms of security and threat modeling, because it just you can't model for full hardware platform one single threat model, because you have a lot of third-party components and you don't understand security and threat modeling about them fully, right? So you just use this IP on your hardware, as example, boot tools stack, network stack, and a lot of others. And also in the same case, you just put in the very trusted place these components, but they can attack differently and gain for the attacker different perspective for the next step for attack the platform. So the system state transition between firmware layers and security boundaries defined by hardware, but frequently verified in the firmware, which is create some level of inconsistency and give some additional opportunities for the attacker. one of the interesting thing I was discovered, it is basically uh, you can disable the boot guard from operating system level during upgrade for Windows 10. So, and this research been already presented in the last year on GrayHat Asia and UpCode 2019. But think about how this works. So you have bootguard technology, Intel bootguard technology, which has been developed to armor secure boot process. So basically, the verification of secure transition and chain of trust start from CPU reset. And okay, let's say everything is configured correctly and it's perfect implementation, but you have platform configuration manufacturing mode, which is can be true. And in this case, verification in bootguard for Dixie volume will be disabled. So what that means, if the attacker inject malicious implant in the Dixie volume and enable this platform configuration data bit and just flash directly to the platform malicious update, it can disable, it can be basically disable any benefits from Intel bootguard because it's just a basically backdoor which is disabling the technology on the fly, right? So complexity of modern firmware supply chain is very, very complex and not controlled by 100% in the single hardware vendor. So that's create actually a very interesting perspective where even owner of the platform doesn't have the full picture and visibility on their hardware. Also, I really like this picture of complexity of UEFI ecosystem, where we have a lot of different vendors. And as example, Intel is own Intel reference code, right? So they are giving this reference code to independent BIOS vendor developers like Phoenix, Insight, and American Megatrends. And these frameworks came to device manufacturers like Foxconn and many others. And basically after that, actually, it is came to original equipment manufacturers like Dell, Lenovo, and HP. So in this case, actually, ecosystem of Apple looks much more consistent because they try to avoid a lot of third parties involved in the development process. But in the same way, for most of the vendors, this supply chain picture actually create a lot of complexity and additional layers. As example, also it is a lot of licensing agreements and DRMs is involved. And as example, if you have outdated code from American Megatrends, you're not getting new updates or even like fixing vulnerabilities from them. And it's create some problems for whole ecosystem because some of the platforms will be just stay insecure, right? And these examples actually show how the ecosystem of UEFI firmwares is broken in this case. And what about good old days with OS bootloaders, right? So we have a BIOS, which is basically boot master volume boot record, and it's passing control to some bootstrap code, and bootstrap code start boot manager, which is start winload UEFI. In UEFI world, you have everything black box. You have a firmware, which is basically a little operating system, which is executes all the stages and then passing control to the operating system level. So basically, it's not a lot of visibility from the operating system level on the firmware side. But secure boot will save us all, right? So what happens, basically, we have, as example, this interesting example of the threat where it is just a simple ransomware, which is block at some point UEFI boot process and raise ransom screen on on your monitor or your laptop. So basically the system just doesn't boot. But if you look on this code, it's just a few lines of the C code, which is compiled as a Dixie driver. Somebody injecting the firmware and flash it as with the physical access, or basically provide some ways of exploit for abusing remotely. So in UEFI firmware rootkits, myths and reality at Black Hat Asia, in 2017, I was demonstrating the way how we can basically create the path of remote exploitation of the system with the different stages, of course, but persist in the end of the spy flash. Also, interesting case with Kaspersky bootloader SINET. So, right, so not in the UEFI ecosystem, we basically don't have controlled blacklist for deprecated bootloaders. We have the blacklist, which is stored in UEFI.org, but how many systems recently downloaded and deprecated of these bootloaders? So basically, I would say SINET, it's not equal trusted. And we learned these lessons on the operating system level a long time ago. But on the firmware level, we're still learning about the same thing happening, which we already been seeing before. It also reminds me MS 16100 presented at DEF CON, where vulnerability allow attacker to install a vulnerable boot manager, basically downgrade the boot manager and exploit the vulnerability which has been already known. So we blindly trust anything which is SINET and come from the trusted source. And it is why, as example, the boot hole vulnerability was so painful, because actually on the UEFI ecosystems for servers, it's been, I would say, this problem's been quite known in the past, but nobody pay attention for it. And one of the problems been found by Dmitry Alexiuk when he basically bypassed the secure boot on the HP ProLand servers with SINET HPCA grab. And basically, he found vulnerability which has allowed him to execute arbitrary code and basically avoid the secure boot on that level. So, yep, it is an example of bootloader, and here is a vulnerability from the grab. The diversity of the open source ecosystem actually bring even more inconsistency to the boot process on the late stages, because first of all, it is a third-party modification, it is outdated versions, it is a hell of the SINET versions, as example, which is vulnerable, but we don't know all of these vulnerable versions, and we just let them go if somebody will be trying to downgrade it, right? So basically, blacklisting in this case will be not really working correctly. Another good example of ecosystem vulnerabilities, it is Intel CSME 2019-90, where it was CSME boot ROM affected. It is unpatchable code, and basically it is allow the attacker to gain arbitrary physical access to the spy and basically create some arbitrary execution code. So it is very hard to make platform secure, but it's even more harder to hunt this kind of threats because it's a lot of unknowns. So the boot time software supply chain only increasing complexity, and we don't have a good solution for that yet. I really like this picture, which has been presented by Rob Wood on Platform Security Summit in 2019, where he say we have this direction of increasing privileges tied to the hardware, but in the same case, the complexity of that attack surface, it's even more, it's even bigger. So, but let's talk about a bit about root of trust. And nowadays, it is it is a lot of companies talking about root of trust tied to FPGA. And basically, this custom root of trust, it is interesting direction for especially for the cloud and data centers. But how this root of trust baked in silicon can be attacked. So first of all, like remember this Cisco Trust Anchor attack from 2019 wood paper, and also from the talk on the DEF CON, where the attacker been able to attack the system and modify spy flash and bitcode of FPGA root of trust. But in the other directions, we have this little bootloader inside the FPGA, which is immutable, right? But not really. So as example, Intel Max 10 FPGA being attacked, and look, I really highly recommend you to look on this presentation from the Hardware I/O, where Sergei Skorobogatov been presenting the way how he can modify immutable bootloader inside the FPGA. Basically, we blindly trust anything which is baked in silicon because we believe what is in silicon, it is secure. But actually, it is creating just more obscurity for us and for the attacker too, of course, but it is not mean what is in silicon, it is more secure. We just understand less about the silicon because vendors try to make these technologies more obscure to us. So, and of course, counterfeit devices or hardware implants, it's not a rare thing. I would say, if you're interested in this direction, look on the F-Secure research where they found fake Cisco's with counterfeit debug ports available on the boards. So, and it was basically the way how you can bypass on all the updates, verification and authentication on the platform. So we really need to pay more attention to hidden attack surface in hardware and firmware and create more transparency and visibility level in this direction. Thank you very much, GrayHat, Con, and I will be glad to answer all your questions.